welcome to video 2. This one, like I said last video, free body diagrams and types of forces. I think it's safe to just get right into it, huh? Okay. A free body diagram, sometimes abbreviated to just an FBD, for simplicity. A free body diagram is just a diagram that illustrates all of the forces acting on an object. This object is usually simplified. It's either represented as a dot or a box. CLS square, whatever. Just simple geometric shapes like a dot or a box. For example, like I might represent a large complex object, like I don't know, like a car. It's just a dot. It's simple, and I can just like draw like forces and all that and whatnot. Now, as you can see by the fact I'm drawing arrows, each force it's indicated by their own individual vector. The direction of the vector indicates the direction of the force. So this particular force, it's pointing in that corner-ish. This force, it's pointing straight down, right? It might be force of gravity because gravity always points down. I'll get into that later. The relative length of each vector represents the relative magnitude of the force. So, for example, if I erase that, if I drew it super long like that, that indicates that this force that points straight down is a lot more than the force that's pointing, this force I just circled, right? Similarly, if this force was super tiny, then the opposite is true. This small force is, this small arrow means that that force is much smaller than the other force, right? Each force also has to be labeled. I'm going to go back to a more normal length. Each force has to be labeled. So, for example, like this might be this force and this might be that force, whatever, right? You just want to accurately label all of your forces. And one final thing is you don't want to draw the components of the force. For example, with this, sometimes it might be useful to like take that force of tension and split it into its components. You might split it into the vertical component and the horizontal component, like the same way we did with velocity, right? But you don't want to split it into a components in a free body diagram. Component diagrams can be useful. They can be drawn and they can be really helpful in certain problems, but you don't want to draw a component diagram for a free body diagram. Though a component diagram and a free body diagram just aren't the same thing. All right, so we now know free body diagrams help us to draw the forces. Well, what types of forces are there? First thing I want to say is that the units for forces are newtons. We know with Newton's second law, F equals ma. I'm going to add the sum. This force, newtons, right? The mass is always in kilograms. That's the standard unit for mass. If you're given grams, you're going to want to convert it to kilograms first. And then acceleration, our good old friend, meters per second squared. We can just draw this, relationship between these units. Anyway, I'm going to get into the forces now. The first force that's probably prevalent in almost every single problem, force of gravity. The force of gravity, I should probably say, force of gravity is this F sub g that I used in this earlier free body diagram. The free body, no, what am I saying? Force of gravity, it comes from an object's gravitational attraction. For example, Earth exerts a constant force of gravity on us. This force of gravity always points straight down when you're on a planet, and if it's like two different planets, like for example, if I have one planet here and the other here, they're gonna point straight to each other's centers of masses. One there, right? Pretend those are the center of masses, okay? Just please. So it always points to the center of mass. Usually, in the case of like when we're on a planet, that's usually going to be straight down. Force of gravity can be given mathematically. Whenever the gravitational acceleration is constant, it's a constant when you're on a planet, by the way. For example, on Earth, it's a constant 9.8 meters per second squared. Some people say it's 9.81, some people round it up to 10, but usually you're fine with just using 9.8. This is going to get messy really quickly, but yeah, so force of gravity is equal to m times g. So the force of gravity, it's literally just the object's mass times the acceleration due to gravity. On Earth, it's just 9.8. And this it's really just Newton's second law. We take the force is equal to mass. G just happens to be the acceleration, in this case, the acceleration due to gravity. This is literally just a rip off of Newton's second law, technically. Um, Force of gravity is also equal to weight, but do note that weight in this case, it's still in newtons, it's not in pounds. Just a conversion factor between newtons and pounds. I don't know off the top of my head, but newtons and pounds are not the same thing. I also hit this in the last video. There is an equation for when the gravitational acceleration isn't constant. It usually isn't constant when, like, it's these two planets. And, like I said last video, it's not important yet. It's going to be more important in later units. But whenever g is not constant, it's this big, long equation. Like that. You don't need to know the specifics yet, but basically g is Newton's gravitational constant, which is about 6.67 times 10 to the negative 11th. I don't quite remember the units of that. M1 is the mass of object 1, and 2 is the mass of object 2, and r is the distance between the object centers of masses. Like I said, though, you don't need to know this this force or this equation so well, but you do want to know mg. In fact, mg is so prevalent that sometimes instead of people might write mg instead of force of gravity. Just as long as if you get your point across, you're fine. It's okay to use fg. It's okay to use mg. You do you. Next force is the normal force. The normal force comes from an object being on top of each other because of some intermolecular uh, reactions and relationships and stuff. I don't know the whole story behind the normal force, but basically, when something is on top of another, they're never actually touching because like the molecules are kind of repelling each other. That's the normal force. This normal force, yeah, it just comes from an object being on top. I should technically put that in quotes of each other. The normal force, it's always perpendicular to the surface. If my surface is perfectly level, and I have an object sitting here, then in the free body diagram, I would say that F of n points straight up. F of n is normal force, by the way. And, I mean, force of gravity would be straight down. If it's on an incline here, then this normal force, it's going to be perpendicular to the surface. So it's going to be about that. Whereas the force of gravity points straight down still, regardless. Random line up here. Now, yeah, in this example, like I highlighted, usually it opposes force of gravity, or in the second example, a component of force of gravity. But, I mean, normal force, it might change, but it's always due to an object being on top of another. It's always perpendicular to that surface. That's the two things about normal force that you're going to want to know. Force of tension is the next main force. Force of tension is just F sub T. Sometimes you might just see it represented as uppercase T for just tension. That's a really big uppercase T. Let me write it a little better. Sometimes it's just T. But the force of tension just comes from tension being stored in a rope or a string. If something is like here and it's hanging on a string and like there's this thing here, right? There has to be a force in the spring, or else, like as we know with Newton's, from Newton's laws, like currently the only force is just mg, right? So if that was the only force, then it would just fall straight down because there's no other force. This is why there's a force in the string, and this force happens to be the force of tension, right? Next force is going to be the spring force. The spring force is F sub S, and it comes from displacing a spring from its equilibrium position. For example, like if I have an equilibrium position of the spring like this, and if I extend it out to about here, then there's going to be a massive force trying to bring it back to equilibrium, right? You probably have experimented with springs in the past, and you know that like the more you extend it, the greater the force is. And in fact, the spring force and the displacement are proportional to each other. This is this proportionality is part of this law that we call Hooke's law. Hooke's law, it just states that the spring force and the displacement from equilibrium are proportional. This proportionality is mathematically represented as the spring force is equal to k times x, where the spring force is F sub s, right? K is the spring constant. Spring constant just gives like how stiff a spring is. The higher the spring constant, the more stiff it is, the harder it is to extend. And x is just the displacement from equilibrium. I do want to note though that this equation, it only gives for the magnitude of the spring force. It doesn't necessarily give the direction of the spring force. The direction of the spring force and the displacement are always opposite of each other. For example, in this little example down here, when I extended the spring to the right, the spring is trying to go to the left and go back to equilibrium position. If I pushed the spring to the left in this case, then it would be trying to push back to the right and return to equilibrium. The two are always in opposite direction. Displacement and the direction of the force, opposite direction, and F's S, Kx. The last major force is going to be force of friction. Force of friction is almost represented with F sub F. Force of friction, as you might guess, it comes from just the prevalence of friction. If friction is present, force of friction is probably going to be present as well. There are definitely problems where it'll say in the directions, assume friction is negligible. In that case, don't include it in a free body diagram. If it's negligible, then the question, it's telling you to like pretend it isn't there. So don't include it in free body diagrams. Don't include it when you're summing forces. Don't include it in your calculations. Whatever. Just don't include it. If it says it's negligible, ignore it completely. If it says it isn't negligible, then you won't consider it. There's a mathematical way to determine the force of friction. Force of friction is equal to the coefficient of friction, which is this fancy little u, times the normal force. It's pretty simple, actually. Yeah, like I said, the little u, it's the coefficient of friction. Usually it's between 0 and 1. 0 means there's no friction. 1 means there's a lot of friction. It's rarely ever 1, but it can get quite high. Yeah, these are kind of the main forces of AP Physics 1. Yeah, I can't think of much else, huh? Yeah. Okay, well, that's it for this video, I guess. Next video, we're going to be looking at Atwood machines. Atwood machines are a really nice way to practice forces, free body diagrams, and some of Newton's laws. If you want to have some practice of free body diagrams, I will throw a link in the description. I believe it's 12 free body diagram. No, it's 12 scenarios, and you have to draw a free body diagram for it. Some of them are a little insufferable, so I don't blame you if you don't try them all, but it's worth giving a shot. Anyway, yeah, I'll just see you next video. We'll be talking about Atwoods then.